It's a great honor that Professor Charlie Wang accepted my invitation to come to the York Robotics Seminar. Actually, I know Charlie from Wikipedia. Actually, it's something for me. I mean, I have actually some overlapping, although it's not overlapping in time, probably overlapping in space with Charlie here. So we went to the same bachelor university, so which is Huazhong University of Science and Technology in Wuhan, and then that's actually where I know him from, because when you search the Wikipedia page of my university, there's one section called Distinguished Alumni, and Professor Wang is one of them. So basically, he is an expert in digital manufacturing and also soft robotics. So also so he received his PhD from Huazhong University of Science and Technology. Then he went on to do a PhD at Hong Kong University of Science and Technology. And then he stayed in Hong Kong as assistant professor, associate professor, then full professor at Chinese University of Hong Kong. And then he moved to someplace where I've been as well, which is TU Delft in the Netherlands. So he moved to TU Delft as a full professor as well for 2 years, I think.
More than that.
More than 1 year. But I don't know. I don't think we overlapping.
No.
Yeah, we didn't. And then he decided to come to the UK, as I did as well. So from the Netherlands to the UK. So he's currently a chair professor in digital manufacturing in University of Manchester, and I visited his lab actually. I think in March, which is fascinating. So what he has been doing is really fascinating. So without further ado, the floor is yours, and thanks again for accepting my invitation.
Thanks, June, for inviting me to visit such a nice campus for University of York. And yeah, right. So let's come back to the title of today's presentation. We're talking about the simulation, sensing, and control of soft robots. So I think it's a good way to really start from doesn't. I'm not sure whether it's work or not. Okay. Sounds like why we want to do soft robots, because the real motivation of that is like, if you consider about a robot which is going to work together with human beings, pretty much you don't want the robots which have a very large stiffness of its rigid body, because basically people feel it's not very safe. So if you're looking at the soft material which is used in the general environment of a human being, which is pretty much in a very low value of Young's modulus compared to those firm material which you're using in those articulated rigid joint robot hand. So we started this project of a soft robot when I working at the Netherlands, because the Netherlands is very very keen to really using soft robot in many of those agriculture applications and also biomedical applications. So we start projects from this kind of setup. And here shows a few examples of soft robot, which is definitely demonstrate the environment of soft robot, like a pick and place of those objects, which is very soft. And also one of the very advanced function of soft robots, instead of the hard body robot, is very good for explore those environments you have no idea about what is really happening around you. Because one major function of soft robot is it's allowed to have a collision instead of the general motion planning of a hard or rigid body of a robot. Articulated robot is allowed to avoid the collision. So basically, soft robot is trying to use collision to explore those unknown environments, and also the material compliance provide a great opportunity to really grasping and manipulate those objects, which have a large variation of shapes and the complexity of geometry. And then here shows one example of why we want to do this, because we are actually a design manufacturing group. But if you're looking at soft robot problems, many of the soft robot problems comes back to the design problem. It's how you're going to design.
Ja, dit is een hele bijzondere hand. 3D geprint, ontworpen door iemand van de TU Delft. Er zitten kamers in en met perslucht bootsen ze eigenlijk spieren naar. En in de toekomst zul je dit in protheses en andere toepassingen in de zorg tegenkomen.
10 chambers. So basically this shows how complicated the channels inside of this soft robot hand, and then how this soft robot hand is able to generate different kinds of displacement, different kind of deformation, and how you're going to well control this deformation. There are a lot of design problems there. This is because at Netherlands, I'm working in the industrial design faculty. And so this gives us a lot of interest to see why we try to using soft robot, how going to manipulate, well control those soft robots. And then this brings a lot of challenging problems as well, is because basically this is not a well-defined problem, and also brings many of those ground challenges, which I would like to highlight a bit in the following slides. But before that, let's consider about what's the conventional robot versus soft robot. What's the major difference? And then the conventional robots, no matter what is articulated robot or delta robots, have limited degree of freedoms. This is a general setup. So that's why we can get all those analytical formulas for kinematics, and it can be using in those control theories trying to control the manipulation or the operation of this rigid robots. If you're looking at soft robot, basically they have a large number of degree of freedom in the deformation, which is hard to control. And then also it have very small number of degree of freedoms in the actuation. Think about the real actuation we have in the soft hand is like 10 chambers. We only have 10 different flow, which can be controlled. So the degree of freedoms in the control or degree of freedom in the actuation is much, much lower compared to the degree of freedom in the deformation, which is quite a challenging problem. And we are trying to really tackle this problem in our research. So here I would like to do a little bit about literature review. Actually, this is very nice literature review, which comes from Daniel Ross' team of MIT. And summarize all those ground challenges of design, fabrication, and control of soft robots. I would like to extract a few of them out to really highlight here. One is like rapid design tool, which is really lack of rapid design tool, because you need to have a simulation-based optimization in the loop of design. Consider about finite element analysis, what nowadays you have. Even for those linear deformation or linear material deformation takes extremely long time. Not talking about the material what we are using here, in general is highly nonlinear. You have a hyperelasticity, just like a silicon, this kind of raw material is really using in our soft robot body. And also it's a means of a fabrication of low-cost soft robots. Of course, we are largely using those 3D printing technology and also some of the existing components which provide the soft and compliance in the mechanism, but still the fabrication is really quite tedious nowadays and it's not really well controlled. And then that brings a lot of problem to the following control issue, because the same file is sent to the same printer using the same types of material, and it generates different deformation behavior in general. Okay. This is because the room temperature, the humidity, all these things will have the influence on the softer body what you fabricate. And then we really also summarize, Daniel Ross actually giving a nice summary about what is the algorithm aspect is really need to be developed, including the sensing, planning, and control. All this brings together a very good topic for the future research. It's like this is how we start from. And then let's talking at one issue. So we start from the design problem. So actually, this is a problem which is quite well studied. And because if you're looking at the finger itself, looking at your finger, you're easy to bend, but you basically don't have the finger easy to twist. But if you have a softer manipulator, softer gripper, which is you define, and using the softer material, it's very easy to have those we call the bi-side or out of plane deformation, right? So it's like this kind of a deformation, making those grasping very unstable, and those objects under grasping easily running out of those grasping behavior. So it's basically, this is something we need to be optimized. And then, so we define our objective function, which is like the force divided by the out of plane displacement. So basically, we're trying to minimize this sort of thing. And unfortunately, the design itself, when we parameterize, you have many of those parameters, which is going to influence the final performance. So the general practice of design methodology is like you need to do a kind of a sensitivity analysis and trying to reduce the dimension. So we are trying to reduce the dimension from 8 into a 3 or maximum 4. So basically, based on this kind of sensitivity analysis, we decide those parameters just like LA and those like a height, all those things, which is given a totally different performance in the grasping. And then we really using this kind of analysis, trying to using data-driven approach to do the simulation by FEA, and then trying to somehow study or learn a kind of a design space representation in the high dimensional space. And then according to those representation, we kind of optimize the performance. And here just to give you one example to show like why design is so important in this kind of soft robot design. If you're looking at those optimized one and the unoptimized one, you find like this one actually gives much better performance of those grasping and caging. And then it's really the same material, the same amount of material. So basically we only change the combination of how you're using those material, which is give you a better performance. And in general, this method can be widely used in many different aspects of soft robot design because you basically using the simulation in the loop to really simulate how the deformation happens, and according to the performance of the deformation, which helps you to really improve the design. Okay, it sounds quite simple, but if you're really trying to really using this in a real-time problem, or you're trying to use it to really predict the behavior of soft robot in the control problem, not only control problem, but also even those simpler setup like a planning problem, you have a lot of challenges. One of the major issues is like finite element analysis extremely slow. So our research then moving into a way like we are trying to develop a better simulation. So basically, let me simply say this. So basically, this simulation will be used as a kinematics calculation method or kinematics calculation solver to trying to tackle the kinematics problem. So basically, we're starting from forward kinematics problem. And then this is a general setup. For those of you who come from a robotics background, you can understand this can be easily calculated by simple analytic formulas. But the thing is, like, if you go moving from rigid robot to soft robot, this kind of relationship becomes highly nonlinear. Does not really give you a good way to really be able to predict the deformation of that. So we need to really tackle this issue. And a bit about literature review. It's like how the people are really tackling this problem at this moment from the general soft robotics area. So one thread of research, they're using simplified model, which is learned from solid mechanics and using differential geometry, trying to really assume, like, for example, it's always have a constant curvature deformation. To me, this is too much simplified because if you think about very complicated geometry, which you can have on the softer body, does not really give you constant mean curvature deformation. But people are trying to say, oh, we are able to really use this to have an analytical solution and trying to use it in the kinematics and also the control. And the other way is like, don't care about those models. We're just using huge data to really feed them into neural network. So this comes about the model-free method, right? But the thing is like, where are you going to get in this data? If you capture from those physical setup, I'm not sure how many of you really have using the motion capture system and really trying to capture the deformation. I can tell this is not practical at all. This is because one aspect, the motion capture system, they have a high requirement on the lab setup and also high requirement on the lighting, everything, okay? The other thing is like the repeatability of deformation in the soft robot itself is not very high. Think about the material itself have a kind of a material level delay. And so every pose, if you want to have a very stable shape, you need to wait there for an extremely long time. I mean, relatively 3 to 2 seconds. And then you have the stable shape. And then so basically every shape can capture every shape takes extremely long time. So this is not practical. So people say, oh, we are going to using FEA. So this is actually the interface we captured from the most advanced finite element analysis software nowadays, widely used in University Research Institute Abacus. Abacus is the nice software which is able to capture highly nonlinear deformation, but it suffers from this nonlinearity, geometry nonlinearity. So we have large deformation, large rotation in the deformation, which is hard to calculating in a short time. And then material nonlinearity, because we have a hyperelastic material property. So those Young's modulus curve is not constant anymore. So it's kind of a highly curved, a different shape of displacement and the stress and strain relationship, right? And then also the actuation nonlinearity. If you're using cable-driven or using fluid like a pneumatic and hydraulic driven the soft robot actuation, basically the actuation itself has a certain level of nonlinearity. So all this nonlinearity putting together, making this problem even more challenging to be solved. So I think we started this project 5 to 6 years ago, and we are trying to really bypass FEA. So this is quite a robotic solution, although I come from design and manufacturing area. So design manufacturing areas, people always seek the help from solid mechanics or fluid dynamics, trying to solve this problem. But robotics guys solving the problem in a different way. They just see, and then they're trying to repeat what they see by a so-called simulator. So this is what we learned from a computer graphics community. They provide a way to really generate a nice animation in their movies. So this is a deformation method they're using by Pixar in their computer animation movie. So we're trying to borrow this idea to here, and then we're able to using robotics method to really calibrate those material properties based on the simulation we're able to achieve. So that is the basic idea. We are trying to, using this so-called simplified deformation model, trying to bypass finite element analysis. Nice part of that is like computer graphics scientists, they're already able to develop those deformation model, which can capture large deformation and large rotation much more easily compared to finite element analysis. Okay, so the simulator we develop here is able to cover different actuation, including the cable-driven actuation, including those the electric elastomer actuation, and also pneumatic and hydraulic actuation. So basically, if you consider about these 3 different types of actuation, all of them sharing one common property is the actuation itself is very easily to be measured by the geometry properties. For example, the cable-driven actuation actually can be measured by the length distance change of the cable. And the DAE is like the electrical elastomer actuation can be measured by the total area change of this area. And the pneumatic actuation or hydraulic actuation can be measured by the total volume change of the chambers, right? So all this actually giving you a direct driven of geometry instead of force. And also the other aspect, if you consider about robotics area, geometry properties is more easy to be controlled and measured compared to the force, because no matter how you measure the force, it's still using electrical signals to really generate those, to measure those force. And then, but for this one, we can easily controlled by motors, can be easily controlled by the like a vision servo, all those kind of things, right? So, and we develop a kind of like divide and conquer method. So basically every element, we just split them out. And then so we evaluate every element separately. So to evaluate what is the total area change, the volume change, and also the difference between its current shape and its original shape before applying loading. And so basically we are trying to minimize the shape difference between the current shape and the shape before apply loading. So according to this formulation, we can easily solving this by a local and global approach. So basically locally deform it one by one and globally blending them together. The nice part of this is like this global blending process is actually can be formulated as a least square solution. So least square solution versus the stable solution can be easily calculated. So basically the iteration converges very fast. Okay. So, and we could further introduce different material properties into it because we are able to provide the parameters to control the allowed volume variation. So if you allow the volume to largely deform, then of course that's a soft material. If you do not allow the material to have a large volume variation, that's hard material. And then relatively, we're able to calibrate what is the coefficient is going to be used in our simulator by using this kind of relative deformation measurement, which can be easily generated by vision system and then provide a good calibration result of the simulator. Okay, for the details, because of the time, I will not introduce them. And some people will ask, oh, you're using simplified model, and how likely your simplified model is going to really mimic and regenerate the real deformation result? So we compare with Abacus. Okay, so this is the simulation of Abacus finite analysis result, and this is our simulation result. We apply the same loading, and then the shape, the same, but the speed, we are able to generate speed like 50 times faster compared to FEA. And then this is still not fully accelerated by graphics hardware yet. So if you apply it to GPU, we can increase speed by around 10 times. Okay, so in general, 500 times faster compared to FEA, which is provide the opportunity you are able to using this simulator in different scenarios, including control optimization, and also like how you are going to really predict the deformation by optimize not only the shape, but also the actuation and also sensor. So in the following time of today, I'm going to keep using this simulation as a core to addressing many problems, including the sensing and control. Okay, so this is very good to also see how difference of this predicted result and the real one. So this trajectory actually gives you like the predicted trajectory of a marker on the gripper and the real trajectory of this marker on the gripper, which is captured by motion capture system. Okay, so you can see like the arrow is relatively small, but for this one, I think the friction actually contributes a lot to this arrow, which is generated by the simulation, the difference between the simulation and the physical setup. Okay, and the other issue, as what I mentioned at the very beginning of today's talk, is like collision is something you cannot avoid in your simulator, because the general principle of the soft robot is like we are going to use collision to really explore the environment. And collision plays a very important role of all those grippers deformation. Think about the single finger gripper, how it's really deformed. It's only because the collision between the neighboring teeth. You only have two teeth which is inflate, and then they're going to collide with each other. And this collision actually give you a much better performance to be able to let the gripper to be bended by using very small pressure. Okay, so using small pressure, you have a large inflation, and then the inflation between neighboring teeth really pushing each other to have a better deformation. It's like more easily to be bended. Okay, so the things like, are we able to really simulate this in our simulator? Okay, so we are using, again, borrowed those expertise from computer science, and then we are going to we're really using those AABB based tree to speed up the computation. But the other aspect, like how you're going to handle this collision, which is very important, because there are many of the ways to handle collision. Some of them are differentiable, some of them are not differentiable. Okay, so why we need to have a differentiable simulator? This is because in the future, we're going to be using this simulator in the whole pipeline of neural network-based optimization and control. So you need to have the differentiable simulator as a building block. So it turns out you're able to easily have those back propagation all the way back to the original control path. So we introduced the virtual spring concept. So virtual spring concept brings you a simulator which can be differentiable. It's much more easier than those like algorithm decided kind of collision response method. Okay, so we have this paper published last year, IROS conference. And then this shows some demonstration about how well it can capture the deformation and the like collision between the neighboring teeth. So you can find this is the real one. The teeth really collide with each other. And then this is another one which have the chamber have a large volume vibration, which is not easily to be handled by abacus kind of FEA simulation. One major issue is like they heavily rely on a remeshing process. Unfortunately, remeshing process is not always stable because of those numerical calculation errors. Okay. So this shows again the time difference. By somehow optimize our code by this version of simulation, we are able to achieve 100 times speed up already, again without the GPU. And then so this is another simulation, and this one have 25 times the speed up. And then this shows another setup of soft robot. Is like software deformable interface, which can be widely used in many of those molding process to have a shape controlled mode in different fabrication applications. I will demonstrate one. And then, of course, there are many others like scenario, those deformable interface can be used in design manufacturing. And so now we have a very fast simulator, right? And then that means we have very fast forward kinematics model. And then are we able to use it in the control? And let's say we're trying to solve in those inverse problems, like we are trying to determine the actuation, which is able to drive your robot into a desired deformed space, okay, or desired deformation, deformed shape, okay? So this shows our setup. We're trying to demonstrate our soft robot simulator being able to really generate simulation, capture the physical environment very well. So basically, this is our setup, and this is our simulation result. We can find like this is really well captured, okay? And then we are trying to use it in the inverse design problem. So basically, inverse design or inverse kinematics problem here is just like optimization problem. We are trying to optimize the setup. We are trying to optimize the actuation. And then so it turns out give you the deformation. So this is quite straightforward problem if your simulator itself is differentiable, okay? And then that's just starting from a very simple setup, like say, mathematics is not differentiable, but numerically, we can easily use in the final difference to really calculate its gradient, okay? And then we just using this simple method in our paper, which published 3 years ago, we're using the final difference already able to achieve a very good inverse kinematics result. Okay, so this is a iteration step of those IK solver. I don't want to go into details. Let me show you a bit of the result, which we can achieve by using this final difference in the inverse kinematics. Okay, so we're using two setups. This is string-driven robot, and that's the pneumatic actuated. And then again, we are trying to avoid the force measurements. We're trying to avoid those force prediction. So we generally using those straightforward kind of geometry-based calculation. And then compared to other simulators, this is a simulator so far, right? So sorry to bring it out. And I don't want to be too offensive, but it's like in real, the SOFA itself is really based on the integration of ODE. So it's like accumulated all the arrows into the large deformation, which is somehow you cannot solve. You cannot avoid it if you're using those ODE solvers. Unfortunately, we're not using fortunately, we're not using ODE. And then so we are not suffer from this issue. We directly using the least square solver. So this is a much better result of those simulation, and then different materials can be supported. It's a different color actually withstand different Young's modulus, material with different Young's modulus used in the forward kinematics. Now we start to demonstrate those inverse kinematics. So you can see like this is a bit misleading, but it's a 3 times speed up. Okay, so you can sense the speed, and then it's like we are calculating those actuation from every waypoints, and then being able to drive the robot to really following the given trajectory as a target. Okay, so this is 2 times speed up, and then this is, yeah. So this is inverse kinematics. How we're able to really drive this soft gripper to really follow the design trajectory you are going to achieve.
And this is basically you don't use any other thing. It's just inverse kinematics.
Just inverse kinematics, nothing else. Okay, so we basically use no sensor yet.
Yeah.
Okay, so in the I hope I have time to complete the sensor part. We also do some sensing stuff. Okay, so this is inverse kinematics calculation, and then that is string driven. And let's go forward in the match. So this is how we measure the volume at that moment. Okay, this is a 3-year setup. So this ranges, the volume can be easily measured because it's again a geometry parameters, right? So we can control the motor and then to really control the volume of those air you compress it in. But one major issue is like the air leakage is really a major issue at that moment. So we change the setup later. But this is still good to really demonstrate how we're really calculating those inverse kinematics. And then this is how the robot is really drive to really follow the given trajectory. Okay, so you can see those ranges and really pushed by the motors to really giving you a certain amount of air you're trying to bump in. Yeah, right. So this is forward inverse kinematics problems already solved. Okay, but only have inverse kinematics. It's not good enough because that one, although already very fast, but still cannot achieve real-time inverse kinematics calculation. So we think about a different way. Say, what about we replace our simulator by a neural network? It sounds like very straightforward thinking, but we're trying to avoid to calculating the Jacobi. So basically, we learn the forward kinematics and the Jacobi mapping at the same time. Because we have our simulator, which is developed by ourselves, we can keep running this simulation many times, and then we're able to learn those Jacobi. And then in this simple piece of work, we're trying to really demonstrate, like with the learned Jacobi and the forward kinematics network, we're able to really achieve nearly real-time inverse kinematics computation. So this shows another piece of work which we also included in this work is like we're trying to really fill the gap between the simulation and the real. Okay, so this is called real sim to real network, which is very simple network and just 1 layer or 2 layers of forward neural network. But you can find that it's captured error very well. Think about like the same design, same printer, but only using different material as filament to really fabricate these 2 robots. And you will find like the error will be totally different. So basically, the simulation result and the ground truth results. So you can see the gap between them are those things we need to capture by a sim to real neural network. But the good aspect of with the simple running of a motion capture, let's say a few minutes, you're able to really capture difference between the simulation and the real, and the fit into the supervised learning, you're able to really fill the gap. Okay. And this shows the Jacobi learning-based method, how we are using to solving. This is our previous one, and then this is the new one. So you can feel the speed difference, right? So this again, this is already 5 times playback, and then this is real time. Okay, and the good aspect of learning a Jacobi instead of a direct learn inverse kinematics, because inverse kinematics basically is not a one-to-one mapping problem. It's actually one-to-many. So learning Jacobi will help you to really easily overcome those singularity issue during the manipulation or the process. Because iteratively, you always drive it to yourself, drive your solver or drive your solution to a continuous solution based on the previous step, right? So with the help of that, so this is quite a challenging issue for those doing singularity analysis, like this is singular region, right? So basically, let's say how you really can easily go through the singular region because the numerical gradient to really drive you to go up. Okay, so because neural network basically have assumption of certain level of smoothness in terms of function. So basically that helps you to really solving this issue. And with the help of sim to real, and then this is the motion capture, we conducted by using the cameras. And then we're able to really realize the kind of interactive control of software manipulator by using this setup. So this is real. This is about how the actuator is really driven by the inverse kinematic solver. And this is robot 1 and robot 2. And both of them are actually the same design, different material, but given different trajectory. When you feed the same actuation, then we need to fill the gap. And this shows the interactive control. So you can see, like, we want to move it here. Of course, you see a certain level of difference. Again, this is mainly caused by the friction between the manipulator and the plate. Okay, so this is actually a 2D setup. It's not really like this because we're trying to avoid the influence of gravity, but still the friction that brings a lot of problems. That's why we have certain level of error between. But you can already see the interactive behavior of this kind of a calculation because this is real-time repeat. Okay, and after that, all those inverse kinematics calculation, everything are all solved in the scenario without any of the loading. Okay, so what about if we have loading there? We need some way to really sense the deformation by using sensors. And then with the help of those sensors, we're able to predict the deformed shape of the soft robot. With the deformed shape, we're able to apply the control to really further operate the soft robot. So in parallel of our inverse kinematics research, we also do some research about how to sense the deformation. So this is called pre-proception, right? So the major challenge of those sensing is like the compliance of the sensor itself, and also to capture, because I know someone of you are doing sensing problem here, and then also capture how we're able to capture the large degree of freedom of deformation and large rotation, how those things can be easily captured. All those are very high challenging issues need to be solved. So our solution for the generation is like we're trying to using cameras or those are lighting or color signals because those are the things less influenced by the force or some other factors. Okay, so this is the first setup. So we're using the color sensors, also using those LED and the LDR, trying to sensing those deformation by shading a light intensity change. And then this shows the one design. We're using 3D printing technology to really print the different color patterns inside of those chambers. So it's like if you insert a sensor here, if you have a different bending behavior, so the portion of the magenta which it can be sensed is different, right? So then your sensor generates different signal, and then we are demonstrating how with the help of this signal, we're really able to capture some of the measurement related to curvature. It's not really the curvature, but again, with or without the loading, we are giving when you have the same shape, and then our measurement give you the similar number or similar values. That means this measurement does not really influenced by the loading. So basically loading-free measurement. So for soft robotic sensor design, it's very important to introduce all those sensing methods, which is loading independent. Because if you have a loading dependent sensor, there's basically you are not have any of the control of those deformation which you want to achieve. Again, we're using neural network and trying to really capture those things. And then I would like to jump into those detailed measurements. So you can see this is again as starting from T delta time. And I feel like this marker are predicted. And then the real markers. And you see like how well they are aligned with each other. The prediction is really predicted by those color sensors we insert at the bottom of the gripper. Okay. It's actually measured very well. So, and this is a real-time playback. then we are trying to generate different distortions. So this is never being a constant curvature deformation. It's a double curve, right? So you cannot really using those constant curvature assumption in this kind of deformation. So it turns out in the other aspect is also proved like the assumption of constant curvature is wrong in the real manipulation of the soft grippers. Okay. And then we further demonstrate like it's have less influence of by the lighting. And I hope it's not stuck in the video. So we change the applied pressure, and when the actuator is interacting with the obstacles, and we are able to still predict the deformation very well. In terms of time, and then I'll just skip it and go into the next piece of work we did. Again, they're using different sensing methodologies to really sense the deformation. Again, this time we're trying to apply some loading there. And then this is another very simple software joint, easily fabricated, low cost, all the components are off the shelf. Since we can easily get all those components assembled together to form a soft robot, no 3D printing at all, okay? So, and then we are putting some of the LED lighting source inside and LDR for the sensor. So basically we're able to predict the deformation very well. And then okay, here comes the result. And then we find like by different loading, we're still able to capture or predict the deformation by sensing signal only. You can see like the gray ones are the ground truth, and the red ones what we predicted. Okay. Although there's a kind of a shaking of the signal instability, but still we're able to capture the status very well. Okay. And this is applied to a joint. And this applies for freeform deformation surface. Okay, so there are 4 chambers, and then we're able to really, those are dots I used by using motion capture to generate the ground truth of the shape for the measurement. And for the real usage, then we have this kind of markers. Okay, so you can see this color map shows the arrow. So you can see actually we can predict the shape very well by using those sensors. Okay. And so we recently started using sensors to provide feedback control. Okay. So, and then we also upgrade our setup of those soft robot and manipulators not on. So it's like we have to stop 2 segments, which is setup of our software manipulator. We call it a flex tail. It's like flex pneumatic actuating linkage, which have 2 components. This is the first generation. And you can find that the nice part of it, it can generate large elongation. So like 3 times the elongation and large bending. So this is the first generation, we can shift almost 80 degrees of bending, but the next generation can shift it. And so the things that we need to have for sensing signal, which can be measured by geometry instead of other measurements. So we are using spring. So we apply some springs here to measure the length variation. And also we're using IMU to really, a gyroscope actually to really measure the tilting angles, all those things. So we have an orientation length, which can be easily measured. But the thing is like how we're able to apply them into the real-time control. So it's very important that you are able to predict the deformation of the soft linkage or software manipulator by using this measurement. Don't forget we have our own simulator. So we're able to using our simulator to really generate large data to really learn a neural network to building up the mapping between the sensing signal and the deformation itself. So with the help of that, and then again, we're adding another layer, which is like a sim to real. We're able to really capture the deformation very well. Okay. So in terms of time, I don't want to go to details. So basically, we really learn this by virtual environment, working together with sim to real. We're able to use it in the real-time control. So basically, our control is again based on the iterative solver together with those ADRC based control for the for the actuation relationship between the actuation and the sensing signals. Okay, for details, I don't want to go into that because of the time. And then this is demonstrated how we are able to, again, this is a bit misleading. It's like 40 times speed up. And I'm going to show you the real time, this which is going to apply in our recent setup. Okay, so it sounds like very fast, but actually not. Okay, but this is used to really demonstrate how large elongation can be achieved by this software manipulator. You can see like 3 times elongation, and then we're using IMU integrated here and spring. If you have a chance to visit us, go into our lab, you'll see like this is the first generation, but this is not operated now. We put it aside. We started working on the second generation.
I
So
saw the first generation.
you saw the first one. You have not see the second one yet. Okay, so this is the first generation. You can see like we can generate a lot of different poles and different actuations, and by this neural network. Now we are trying to apply it into, say, to compare the prediction with and without loading, which is very important, right? You need to have very accurate prediction even after you apply different loading onto the same setup. And then this is without loading. You can see like predict result and ground truth match very well. Now we start to apply different load. Okay, this is a lighter ball. Okay. And to further enhance, we apply more heavy objects now. This is more heavy. And then we would like to further increase it to test the limit of this measurement based on the sensor. Now it's like 500 grams. Right, so we started 50 grams, it's 100 grams, 500 grams. And then the reviewer asked us to further challenge it by using some of the like bilateral loading. So we tried, and sounds like still good. So we really appreciate the reviewer's requirement is like to add this into our paper. It's really demonstrate how good the measurement is. So, and then now we're trying to use it, like we have the sensor, and now we're trying to use it in the trajectory following setup and experiment. Okay. All right, how much time I have?
No, it's good.
Okay, so I think I hope I can finish in 5 minutes.
You have 10 minutes.
Okay, so I think this is setup, and you can see like it followed very well. Okay, so I think this is very important to have all this integrated together to really achieve a real-time usage of software manipulators. Okay, and this shows our recent setup. So this is version 2 of our flex paper. So you have 3 joints. So you can see how large the bending can achieve and the elongation. And then now we're doing real-time pick and place. Okay. So of course the bump we pick is a bit weak, so you can see a kind of a shaking at this moment, but this I think can be controlled and very improved in the future. So in this new setup, we have 3 linkage, which provide even larger kind of working envelope, large elongation and large bending, and then with the sensor integrated. So in this version, we remove our IMU, because IMU is kind of strongly influenced by those magnetic field around it, which is not stable at all. So we're building more springs. So with more springs, we're able to also predict a large deformation and the bending and rotation. So, and then we'd like to introduce a bit of the other projects conducted in my research lab by using soft robots for design and manufacturing. So basically, this is for the sustainable manufacturing. So basically, we are using deformable robot working as a mold to fabricate, tailor-make, customized garment by using the bio process. Okay, so it's like recyclable or recycled material, putting them together, simply saying just like growing a mushroom on top of a mannequin. Okay, and this mushroom will become a cloth. Let's simply say this. Okay, this is invented by my collaborator, which is from Netherlands again. And our contribution is like we develop a deformable mannequin, which is able to deform a mannequin into the client shape. So again, this is how you have the chambers really integrated together. You're trying to deform it, but how you're able to achieve kind of a shape control. Again, this is inverse kinematics problem, but this time we're not control one point. We're controlling the whole shape. We want the shape as a whole really approximate the client shape. So let's say you have a client, you come to a 3D scanner, you scan your body shape, and on the other side of the wall, you have a mannequin really can deform it into your shape, and you really fabricate a garment on top of that mannequin. Okay, so sounds like crazy, but the crazy idea gives you a EPSRC fund. So that's true, I think. And then we were lucky to get a EPSRC fund to working on this. And then so this is again the first generation. I don't have time to really compile a second generation and put it here. But if you come to our lab, welcome to visit us. You will see the second generation is much more advanced compared to this one. Okay, and then the syringe leakage problem. So we are trying to solving those motor issue or the actuation issue. So we developed this open pneumatic actuation system by ourselves. So basically, this is open source. You can simply download the file, place the order of this component, and repeat all this setup here, because this is everything we make it accessed by everyone. So basically, go to this link. You're able to have those easily controlled Python interface, programmable pneumatic actuation system. So we're using this to really generate this kind of a fancy setup or of the rocker scissor kind of a game. And also we applied it for the soft mannequin. Okay, this is some demonstration about how the open new can be really used to drive the soft gripper. So if you were interested about doing soft robotics research, and you can easily download these files and trying to building up your pneumatic actuation system very easily. This is very safe setup. You can using it in the domestic environment because we designed it to be used in out of lab setup. So you don't need to have a high pressure really provided for them. It's actually low pressure control. So this is good for the general usage of pneumatic actuation for soft robots. Okay, so I would. Again, this is demonstrate. I think this is important because this syringes, and you have those syringes, you have the air leak. And then when you go into a large deformation, it's hard to sustain the shape. So you can see like the syringe go up, and then you have air leak happens, it start drop. Okay, but we said this open U because you're using flow control. It's more easy for you keeping generate those air to bump in, and then that gives you better control of the pneumatic actuation. So in summary, I'm very happy to share with you guys about our recent research and trying to using a geometry-based simulator as a core, and we apply it to different problems like inverse kinematics, real-time control, asynchronous learning, all based on a good simulator. So as long as you're a good simulator, you really have a very important setup which is able to help you to really tackle different issues. And recently working on using the differentiation property of this simulator to have a better setup or better design for the sensing distribution and chamber design, all based on a good simulator which can be put in the core of optimization. Okay, so here we just demonstrate like using optimization to solving kinematics problem, but you can also use it to solving design problem, sensor distribution problems, okay, or you're picking the number of sensors. All these issues can be solved. But of course, there's much more challenging issues need to be tackled, like a tailor-made deformation and customized mechanical properties. Recently, we see a work that really able to achieve a design displacements and stress distribution, and then that is somehow you heavily rely on good simulator, which helps you. But the good thing is like we're making everything open source. So if you're interested about using our simulator, just go to the website and download it and use it. Okay, we open everything. So, and At last, I would like to thank my team, actually, some of them from Delft and some are from Manchester, and my collaborators and funding agencies, EPRC. We are supported by EPRC and Innovate UK and different universities, and especially Manchester, giving me a very nice, generous kind of professor startup fund. And also we collaborate with Airbus and Voyager automation in some of those research. And this is just demonstrates some research highlight of our lab. Starting from some robotics in this video, it's going to also tackle some other research we done in robot assisted additive manufacturing. We'll spend 1 minute on that. So this is all what you see just now. Okay. But the other thread of our research really go for real, industrial robot-based manufacturing, including biomanufacturing. So yeah, really in live tissues. So look at the line. And continue carbon line fabrication, that will Airbus on that. And hybrid machining this is innovative project. And robot is 3D printing. We got a few best paper award. This is only one best paper award based on this last year. And thanks to and then this demonstrates like what we did in our digital manufacturing lab. So one aspect, we do a lot of soft robotic stuff. The other aspect, we do a lot of 3D printing stuff. Okay. And then this is the most recent research. This caught a lot of attention in the last week. And because we just make it ready. And then we actually using curved layer following the stress distribution and then trying to maximize the performance of continuous carbon fiber. So compared to those planar layer-based carbon fiber fabrication, we can achieve around 5 to 6 times breakage. I mean, those breaking force compared to those planar layer-based fabrication. So Airbus is quite keen to that. So that's why they sponsor us project. And I'm lucky, based on this idea, I get the EPSRC Open Fellowship this year. And then so we could focus on this. So you can see the difference. 5 times. Okay, the same amount of a continuous carbon fiber used in the fabrication, but just using different way to really fabricate it. Okay, so I hope I'm not running out of time, and here comes the end of my talk. And I'm happy to answer your questions, and also welcome all of you have a chance to visit us in Manchester. Okay, thank you.